Section 7.5. If you've gone through all 4 sections already, this is going to be easy. Seriously, this is easy. There's only one trick to it, and I know the trick. The bad part is it depends on what kind of technology you use. With some technology, you have to look at the left part of the normal distribution. And others, you have to think about the area on the right side. Yes, it's a little bit backwards. All right, so this is the end of chapter 7. And I know hypothesis testing for variance and standard deviation doesn't get you too excited. Well, it doesn't excite me either. But there is a little bit to be learned because it increases your understanding of the first 4 sections. These are the 2 things we're going to do. We're going to find critical values. That sounds familiar, right? But it's for a chi-squared test. I didn't mispronounce it either. That X that you see is the capital X or capital Chi for Greek letters. And yes, the square is always up there. The X or the Chi is never by itself. So critical values for a chi-squared test. And second, you want to use that chi-squared test to test the variance, right? So let's get the old pen rolling here and see what we can learn. Okay, so the pen's working. Here we go. Some of these will sound really familiar because we've been doing them all chapter long. Specify the level of significance, alpha. And just a small reminder for you. Remember that alpha, if someone talks about confidence instead, no problem. You just take 1 minus the confidence level and you've got the level of significance. Degrees of freedom, this should sound familiar again too. In section 7.3, we were talking about when we were working with a mean and we didn't know the population standard deviation. We had to go with degrees of freedom and use a t-distribution. Well, this is a little bit similar. N minus 1. Does it get much easier than that? All right, this should sound a little bit familiar too. You can find those critical values for a chi-squared distribution in Table 6 of Appendix B. Okay, now this is a little bit weird. I'll tell you right now. You can see that we're going to talk about right-tailed test, left-tailed test, two-tailed test. All well and good. The catch is, up to this point, until now. Until now, if you had a point right here, that point, the critical value would correspond to this area right here to the left. If you have a critical point here, point number 2, the area for that one, when we use the inverse function, would be everything to the left. One thing that is bothersome about this is that you have to do the exact opposite to use these tables that are found in the back of the book. But if you've done okay to this point, you probably won't have too much trouble making that sort of adjustment. Just remember, the chi-squared test, your pictures are going to seem like they're backwards. And that's what it looks like. The chi-squared, by the way, as you'll notice, doesn't look like it's normal. And it's not a normal distribution. Whether it's for a left-tailed, right-tailed test, a left-tailed test, or a two-tailed test. Some of those things sound familiar, right? Remember, for a one-tailed test, you have an area of alpha. Another one, and for a two-tailed test, we split that alpha in half. And that'll help us find this left critical value and the right critical value. The catch is, to find this point right here, we're going to have to use the area to the right of it. If we want this critical value, we'll have to find everything to the right of that one. That looks familiar, right? But anyway, that is the big difference. So let's try this. We're just going to start with finding critical values for our chi-squared. And for this one, we're going to use a right-tailed test. So why don't we start with a picture? Now remember, this has a tail that always goes to the right for chi-squared. It's a right-tailed test, so we're looking for chi-squared critical point out here. And I'll make that bigger so you can see it better. Chi-squared, and we're looking for what will be on the right. And we'll be looking for the area from this point right here to there. And in this case, since it's only on one side, this area is going to equal the level of significance. That's pretty nice. And what we're going to do for this particular one is we're going to use an n, or a sample size of 26, and an alpha of 0.10. So we can sneak in this 0.10. Now, all you're going to need is that, and the degrees of freedom, and all you have to do is subtract 1 from n. We'll have 25 degrees of freedom. And then you go to the table, and let's see. I can't remember what the table was, but that's not important right now. I think it might be 6. All right, so degrees of freedom, 25. The figure shows that, and we're going to use the area here. And so you're going to look in your table, and you're going to find the alpha value up here and degrees of freedom down this way, and at the intersection you'll find your chi-squared critical value. Yes, I'm sticking with that notation. I like it. Now what you might want to try to do, yes, it was table 6. How about that? I got it right. Table 6, Appendix B. You might put out a little post-it there so you can get to it easily. The critical value is 34.382. See if you can find that. Remember, across the top, look for an alpha value of 0.10. Go down on the left side to a degree of freedom of 25. At the intersection, you should find this number, and that's your critical value. So try that. In fact, hit pause. Try it yourself. Even though you've seen the answer, try it yourself. If you don't get it, try it again. Try it a third time until you actually find it. If necessary, stop by the office and I'll show you. In the meantime, when you come back, all right, so I'm assuming you had maybe a little bit of a success, but at least you tried it. So we're going to find for this one a critical chi-squared value. In other words, chi-squared critical value, and this will be on the left side. So actually, sometimes you might see it like this with an L there instead of C for critical. That way you know it's a left-tailed test. Now, n equals 11 means the degrees of freedom is 11 minus 1, which is equal to 10. And your alpha is 0.01. So in the table, you look for 0.01 up here. You look for degrees of freedom of 10 here, and go sort of like this. And that should give you your magic number, your critical chi-squared value. So degrees of freedom 10, And there's your picture. Remember, it was on the left. But remember too, this is a tricky thing. In the past, we've just used the 0.01 in the table or in our calculators. For this one, though, we have to, if we want the critical value here, we have to use the area from there to positive infinity. And since this part back here is 0.01, the part of this will be 0.99 is the area you'll need for this left-tailed test. And if you give it a shot, as I hope you do, you'll find in table 6 that you should get a left-tailed critical value of 2.558. Now I had to throw this in. I'm not bragging because I use TI Inspire, but I was checking with the TI-84, you're out of luck. It doesn't have an inverse chi-squared value. However, on the TI Inspire, it actually does. Not only that, I hate to tell you this, but you're going to wish you had a TI Inspire for a while. Because on the TI Inspire, of course, your picture looks like this because it has a tail to the right, and we want an area of 0.01, and if this is the area right here, then you're going to put 0.01 because these give you areas on the left side of your critical chi-squared value, just like in the olden days. Now if you're using the table wants an area of 0.99. I hope this doesn't confuse you, but some of you may have a TI Inspire, and you have a right to be thrilled. All right, now we've got a two-tailed test, so we're going to have to do it both ways. We're going to start with a picture. We've got an area out here, so here's our chi-squared on the right. You'll have your chi-squared on the left. Remember, if you're using the table, this one will need an area. And remember, this 0.05 is split between the two, so you have 0.025 on both sides. So for this value right here, since 0.025 is on the left, what you need is 0.975 to put in, because you need the area to the right of that critical value. On the other hand, for the right side, your area to the right is 0.025, and those will give you your two values. This one will be the smaller critical number, and this will be the larger one. Give that a shot. If it doesn't work, try it again. So, degrees of freedom, 9 minus 1, you have 8. And you've got shaded areas of alpha over 2, so you have 0.025 in each tail. And the two areas for the right, 0.025. For the left, it's 0.975. And here we're talking about the table values, table 6 to be exact. There's our picture, and there are our two critical values, one on the left, one on the right. And you might want to try that on the TI Inspire as well. Remember, there is, and excuse me if I don't have this exact right, but you can figure it out. Inverse chi-squared will be your function, and you can find that in the distribution menu, the same place you looked earlier to find inverse normal on the TI Inspire. Remember, for the TI Inspire, use the values on the left. So this one will be 0.025. This one will be 0.975, the area on the left. All right, now we're getting to the chi-squared test itself. We use it for testing a variance. And remember, the variance is not the standard deviation, it's sigma squared. And the standard deviation is sigma. But we can use the chi-squared test for both of these. And as you maybe could guess, the chi-squared test value will have a value, and since we have variance or standard deviation, there's going to be squares out here. We'll see that in a minute. Now, the population has to be normal. Don't forget. We're stuck with that most of the time. The test statistic, S squared. Remember, for the mean, it was X bar. For the variance and the standard deviation, the test statistic is actually the same thing, S squared, the square of the sample standard deviation. The standardized one is this. Not real complicated, I don't think. So there's your test statistic. You have n minus 1, which, remember, that's the degrees of freedom. And your S squared goes up here. That's what you got from your actual sample. And down here, you'll have the variance for the population. All right, so what are the steps? First of all, make sure your sample is random. If it's not random, you're up the creek. And this one, as in a lot of the other ones, it needs to be normally distributed. Now, as opposed to the mean, you had to have certain conditions to make it normally distributed. This one, it has to be normally distributed to begin with. Next, get the claim. The claim and the opposite of the claim. You're going to write those down mathematically, and then you're going to separate them into the null hypothesis and the alternate hypothesis. And as you might guess, the null hypothesis is the one where you see the equal sign. Next, figure out what your level of significance you're going to use. If you're talking about, someone talks about the confidence level, remember, C is, alpha is 1 minus C, and that gives you your alpha, the level of significance. Next, degrees of freedom. That's pretty easy. That's pretty darn easy, right? Number 5, get the critical value, either table 6 or excuse me, if you're very lucky and have a TI Inspire or borrow one, you can find it using that way. But remember, don't jump between table 6 and the TI Inspire because they work opposite from each other. Number 6, where's the rejection region? Why? Remember, you found the critical values because you wanted to figure out what the rejection regions are. Then you'll get the standardized test statistic. This is going to tell you, okay, the chi-squared test statistic is what? Where is it compared to the critical value? Less than, equal, greater than. This is what you're going to compare with the critical value. And don't forget, draw that picture because that'll show you where the rejection regions are. Next, as usual, make a decision to reject or fail to reject the null hypothesis. Once you've got that, then you have to look at what was the original claim. Remember, when you do the null hypothesis and the alternate hypothesis, you label one, the correct one is the claim. That way you can interpret the decision talking about the original claim. It's all about the original claim. Can you support it or can you not? Okay, finally we get to an example. We're going to have an example here. And notice first of all, look for the claim. And second of all, in this section, notice we're working with the variance and the standard deviation. So which one are you interested in? Well, in this case, you're talking about the variance. So you're talking about the population variance, the sample variance. And that's the variance in the amount of fat in the whole milk. And the claim, let's put it up here, claim is that the variance, sigma squared, is no more than 0.25, which means no more would be less than or equal to 0.25. Right away, what's the opposite of that? The variance is greater than 0.25. And then you'll separate those into the null and the alternate hypothesis. The null, of course, will be this one because it has the equals. The alternate, it's the remaining one. You can't go wrong. Now, how are we going to do this? Well, we're going to take a random sample, and our sample, you notice, 41 milk containers. So n equals 41. And are you thinking ahead? Yeah, degrees of freedom equals 40, right? And you've got a variance from your sample s squared of 0.27. And we've got an alpha or level of significance of 0.05. And we're going to assume that the population is normally distributed. Without that, we can forget about the whole question. So here's our null hypothesis, as we found. Label the claim there because that's the claim, and you've got your alternate hypothesis. It's a right-tailed test. Of course, the alternate tells you what direction is that hit. It points to the right. So your rejection region will be over here on the right. You've got the level of significance, and this area right here is going to be 0.05 because it's not a two-tailed test, so you don't split it. It's the whole thing is out there. And the degrees of freedom is 40. Just subtract 1 from n. And then, what's the critical value? Well, find it with the table or your calculator, whichever you're able to do. It's on the right, and here's your critical value you find, and that means that even before you do anything else, the test statistic, you're going to see if that's greater than 55.758. Now you calculate the test statistic. What is this? Well, here we go. The test statistic is n minus 1. That's 41 minus 1, or 40. S squared, we're given that straight off. So 0.27 from the sample. We're comparing it with a variance of 0.25. They're already squared, by the way. Notice, we already are working with squares, so we don't have to square anything. And we get a test statistic of 43.2. Okay, is it greater than 55.758? Nope. What does that mean? about our null hypothesis. We're not going to reject it, are we? It's not in the rejection region, so you'll fail to reject the null hypothesis. What does that mean about the claim? There's not enough evidence at the 5% level of significance to reject the claim that the variance is no more than that. So if someone asks you about the amount of fat in the whole milk, you're going to say it's no more than 0.25. Shall we try another one? All right. So this time, remember in the previous one we just finished, we're talking about the variance. Now we want to be able to go both ways. So here we're talking about the standard deviation, sigma, and it says the claim is that standard deviation is less than 1.4 minutes. So the claim is that the standard deviation is less than 1.4 minutes. What's the opposite? Greater than or equal to 1.4 minutes. Now we sorted out. The null hypothesis would have to be this one. So the null hypothesis will be sigma is greater than or equal to 1.4. The alternate hypothesis is that sigma is less than 1.4. And we'll label this as the claim so we can keep track of that. Now, what do we get from our sample? First of all, we have a sample of 25. And if you want to jump to conclusions, go ahead. The degrees of freedom will be 24. From our sample, we found 1.1 minutes, and we're using a level of significance of 0.10. We need a picture, don't we? Well, if we look up here at the alternate hypothesis, it's a left-tailed test. So let's get a picture in here. The left-tailed test will look like this. So our critical chi-squared value on the left will be here. And the area we're going to be looking for, since the level of significance is 0.10, this is 0.10 out here. But if we're using the table, we're going to use 0.90 because the table uses areas to the right of our critical value. All right, there's our null and there's our alternate hypothesis. The claim is the alternate. It's a left-tailed test. Level of significance 0.10. Degrees of freedom 24. You're good at degrees of freedom, right? Critical value. Just remember, your critical value is here of chi-squared, and this is 0.10, so in the table you would use 0.90 table. If you use the TI Inspire, you'd be using this instead. Make sure you're able to find this 15.659. You can't do without it. So the test will be, is the chi-squared value that we find from the test, is it, remember this is the rejection region, is it less than the chi-squared on the left, our critical chi-squared value, which in this case was 15.659. Now, you need to find the chi-squared critical value for your test, or excuse me, your test value, and -1 degrees of freedom, good. Remember though, we're going to have to square S and square sigma both, because that's how chi-squared works. So if you already are working with a variance, you don't have to change those. If you're working with a standard deviation, you have to square them to get the chi-squared test statistic. Well, there's your chi-squared test statistic. How does it compare? Is it less than 15.659? Yes. So reject the null hypothesis. What does that mean? We found the value was over here. It was close, but close doesn't count. It's to the left of that critical value. So there's enough evidence at the 10% level of significance to support the claim that the correct office and amount of time is less than 1.4 minutes. Shall we do one more? Why not? Okay, first of all, you look for the claim, right? And it's variance. So be careful. Don't get variance and the standard deviation mixed up. We're talking about the claim says the variance, which is sigma squared, is 15.9. Is will be equal 15.9. Now you can tell right away that's going to be the null hypothesis. So what's the alternate hypothesis? What's the opposite of that? Oops. We're talking about the standard deviation. How come none of you spoke up? Okay, so the null hypothesis, it's equal to 15.9. Alternate, it's not equal to 15.9. So we've got a two-sided test. We can draw a picture. Remember, it has a tail to the right, but we're going to have two rejection regions. We're going to chi-squared value on the left, critical value, and we've got a chi-squared value on the right. So you have to find those. Now, your level of significance is 0.05. This is a two-tailed test though. So the area out here is going to be 0.025 and the area out here 0.025. Now if you're using the table 6, what do you need? Well, first of all, for the left tail, you need the area to the right. So area for the left-tailed test will be 0.975. The area for the right critical value will be 0.025. The area to the right of that critical value. Can you find it from the table or from your calculator, whichever applies? Alright, so what do we have? It says a random sample has a variance of 21.8. Oops, I goofed, didn't I? Go back and fix that. So we're talking about variance. So variance, okay, and I guess that's all we need. So we're going to find those values for our variance, the chi-squared value, and we're going to use the alpha split again. Is there enough evidence to reject the claim? Now we're going to assume we've got a normal distribution. So what do we have next? Well, we have to find those two critical values. We have to find out what this chi-squared is on the left and what the chi-squared value is on the right. Those will be our critical values, and these will be our rejection regions. So there we go. Variance equal to 15.9, variance not equal to 15.9. Two tails. Level of significance, that's easy, right? Level of significance, 0.05 split in half. And here are critical values. This is the one on the left. This is the one on the right. So what are we looking for? We're going to reject the null if our critical value on the left is less than 5.629, or we'll also reject it if our test statistic on the right is greater than 26.119. So what is the test statistic? Our test statistic, when we use the formula, is 19.195. How does it compare? Oh, it's not less than 5.6. It's not greater than 26.119. So not going to reject the null hypothesis. It's not in either rejection region. So there's not enough evidence at the 5% level of significance. Remember, the wording is important. Write that down somewhere. Regardless of where you take the test, you can take some of the samples of these wordings so you can get it right. And it's the good wording. All right. Well, if you've made it this far, I'm really proud of you. And next, it depends on the timing, but we might be headed to chapter 9 next. And that will be about correlation and regression. In the meantime, we'll see you in class. Bring your questions. Goodbye.